All right, let's talk about rigid body motion. So when we say rigid body motion, we clearly understand that we're talking about bodies that the motion of objects that cannot distort in any way. Of course, strictly speaking, it is impossible for any object to be undistorted throughout the motion. They always distort. But many of the objects that we encounter in daily life actually almost approximately don't distort. They almost don't distort. So it's a good approximation that we make in order to be able to analyze the motion in a more concise manner. Of course, if you think about how to you can make a thought experiment and try to imagine how you would explain a motion of a rigid body as opposed to a body that can flex or distort. And you will immediately begin to realize that bodies that do distort or that do flex, they are difficult. Their motion is more difficult to analyze because you cannot. You cannot direct your attention to just a bunch of points, maybe a handful of points on the rigid body, and deduce the motion of all the points on the body if the body were able to distort. Okay, so in our discussion, we're going to talk about bodies that cannot distort, and how do we define such a motion mathematically is the first object that we're going to attack. Or the subject that we're going to talk about. Now, let's remember what we do when we're trying to analyze particle motion, right? This comes earlier in our university curriculum where we talk about kinematics and dynamics of points. Well, in order to describe the motion of a particle, you might want to put a coordinate system on the Earth. Maybe something like this, this is Z, this is Y, this is X, let's say, and this is a coordinate system that's fixed to the Earth, right? So, and then you have a particle here, and to describe the motion of the particle, you draw a position vector from the origin of our world frame to the particle, and call that P of t, and its coordinates would be in this coordinate system. Its coordinates would be given by x of t, y of t, z of t, of course t denoting the time. And once you keep track of these three numbers with respect to this coordinate system, you will know where the particle is for all time. That's for a particle. Now, if we try to extend our definition from one particle to a continuum of particles, right? So let's suppose we don't have just one particle, but what we have is a rigid body, right? And this is one point on the rigid body. How should we extend our definition of P of t here such that we keep track of the motion of the rigid body? You might ask yourself. Well, so the starting point for such an analysis is that you pick another point. So let's suppose this was P, right? We just said, let's suppose this point is P. Pick another point on the rigid body, Q, okay? If you pick any 2 points, such as P and Q, actually, they need to satisfy a constraint, okay, for this to be a rigid body. And that constraint is that the distance between these 2 points, P and Q, cannot change as the body undergoes an arbitrary rigid body motion. Of course, this is not true for bodies that can distort. For bodies that can distort, the distance between the Euclidean distance I'm talking about, of course, the Euclidean distance between 2 points can change, but for rigid bodies they cannot. How do we write that mathematically? Well, we say that the norm between P and Q vectors. Now this is the, you can think about this vector right here as the vector P, and this vector right here as vector Q. Yeah, the distance between these two vectors is equal to what they were at the start of time. And so this is essentially a constant of motion, right? Okay, so this equality, of course, holds for any 2 points that are on the rigid body you see. Okay, that's the point here. Now we define rigid motion, right, as a motion such that the distance between any 2 particles remains fixed at all times. Okay? All right, very good. So that's a nice definition, but it's not a very functional definition. So what we're going to see in a few moments is that a rigid body motion, or what we call a rigid displacement, otherwise, may consist of a translation and a rotation, okay? And if you combine one translation and one rotation, then you can express any rigid body motion. That's the nice thing about rigid bodies, analyzing rigid bodies. So let's suppose we are talking about a subset of a three-dimensional Euclidean space. Let's suppose O is a subset of the three-dimensional Euclidean space, okay? And we're trying to understand the motion of this subset O. This is like, of course, a three-dimensional, an object that lives in Euclidean space, okay? What do we mean by that? What do we mean by a rigid body transformation or rigid body motion of this body? Well, what we mean is a function g of t, of course parametrized by t, okay? At each time you get a function that maps this subset O into R3, okay? So essentially, suppose at g of 0, this gives you one transformation. At g of 1, it gives you another transformation that corresponds to the body's current position within the world, okay? Within the given Euclidean space. Now, given 2 points, like P and Q here on this figure, we can make a vector out of these 2 points. That vector would be, say, for example, Q minus P, which would be the vector that I have drawn by the purple color here. This vector would be given by, let's say, V equals Q minus P, right? So this is a vector, and every rigid body transformation, like the one that we just talked about here, that maps O into R3, induces an action on vectors in a natural way. Then we call that, essentially in differential geometry, we call that the push forward of G. But whatever it is called, the symbol is G sub star, and this action on the vectors can be easily written by G of P minus G of Q, where of course, the way I've written this, I guess, I'll just parameterize this map by T. So the parameter I'm going to write this right over here. So essentially, of course, it is going to be for every T, you're going to get a transformation, pretty much is what we're talking about. Then we suppress its dependence on T, essentially, okay? In any case, given this transformation, you can essentially talk about an induced transformation on vectors, and it's given by if the vector, let me see. If the vector V is given by Q minus P, then the action of the rigid body transformation G on this vector V would be equal to G of Q minus G of P, okay? That's the long story short. Okay. Now, if this G gives us our rigid body transformation, and we said that rigid body transformations must preserve length, okay? Then we define the rigid body mapping rigorously as follows. We have a mapping G from R3 to R3. This one is a rigid body transformation if it satisfies the following, okay? If the following holds. Or let's say there will be more than one, so the following hold. One of them is that the length is preserved. Length is preserved. In other words, if you take 2 points, G and P and Q, then G of P minus G of Q is going to be equal to P of the norm between the norm of the vector that goes the norm of the vector G of P minus G of Q is going to be equal to the norm of the vector P minus Q. Okay, this is for all. This is a for all symbol. For all. This is for all P and Q in R3. And the other thing that needs to be satisfied is that cross product is preserved. Okay, this means that the body cannot be, parts of the body cannot be reflected along a line. This is that constraint. You can rotate, but you cannot reflect points in a rigid body. So this is given by this induced map G push forward of G to apply to the vector V cross W must be equal to G of V cross, G star of V cross G star of W. For all vectors VW in R3. You see there's an inherent separation between points in a Euclidean space and vectors in a Euclidean space. This may not have been very apparent in your earlier courses, but this is indeed a very important distinction to keep in mind because points typically transform differently than vectors. Okay, even though you can make a vector out of 2 points, a vector is not necessarily. So let me say it this way. It is not always possible to create the set of all vectors as a difference of 2 points. Okay, even though in a Euclidean space that's possible, in a more general structure of a space, like think about a sphere and let's talk about vectors that live on the sphere, right? Then you cannot really think about that vector as a difference between, as the usual vector difference between 2 points in the ambient space R3. Okay, so there is a natural distinction between points and vectors. Okay, in any case, for this course, you can think about a vector as a difference between 2 points, and then talk about this push forward of G as applying to such vectors. But in general, there is a difference, and it is important to conceptually separate these two notions of points and vectors. Okay, we'll talk about that a little bit further later on. Now, so we'll talk about, this is the general theory of rigid body motion, and whenever we're keeping track of a rigid body motion, right, what we're going to do essentially is that we're going to attach a coordinate system not just to the Earth like this, but also to the body. So we're going to have a body coordinate system like X body, Y body, Z body, as well as the world coordinate system, X world, Y world, Z world, okay? And we're not only going to track the motion of a point on the rigid body, but we're also going to track how these vectors that we designated as a coordinate system that is attached on the body, how the vectors that make that coordinate system up actually move with respect to the vectors that make the world frame up. Okay, we're going to make that precise in a moment. But before we make that precise, let me tell you something that's very important, and it is always going to be true. One thing that's always going to be true about these vectors that make up a coordinate system is that those vectors will always have unit length. Unit length means, the usual Euclidean norm of xb, yb, zb, or really norm of xw, norm of yw, norm of zw. All these things will be equal to each other, really, and the norm will be equal to 1. So all of them will be unit vectors. They will be mutually orthogonal. In other words, what does orthogonal mean? That means they are perpendicular to each other. But of course, the set of b vectors are perpendicular to each other, and the set of w vectors are perpendicular to each other. In other words, xw.yw equals 0, xw.zw equals 0, and yw.zw equals 0. And also xb.yb equals 0, xb.zb equals 0, and yb.zb equals 0. Okay? These are always true, but notice that xw.yb does not necessarily equal 0, okay? So that's not true. Within the same coordinate frame, though, the vectors, the set of vectors that make up the coordinate system, they are mutually orthogonal. One more thing that's important is that these coordinate frames always respect the right-hand rule, which essentially says that if I draw a circle like this and place xb, yb, zb by going counterclockwise like that, this is the positive sense of rotation, okay? Then if I go this way, xb cross yb, I must get zb, okay? This is also true for the set of w vectors. Any coordinate system, it is true for any coordinate system. Similarly, I'm going this way again, yb cross zb equals what? The one that remains, which is xb, and since I'm going the counterclockwise direction, it is positive xb. Similarly, zb cross xb equals positive yb. But notice, if I went, for example, the other way, clockwise direction, and did, for example, xb cross zb, I would get minus yb. We can also, of course, also deduce this by using the anti-symmetry property of cross product, right? The cross product satisfies the following notion. If you take two vectors and take the cross product of them, this is going to be equal to negative of the, if you change the order of the multiplication, w cross v, then v cross w essentially is minus w cross v for any vector, for any vector vw in the Euclidean space R3, okay? Okay, so those are some remarks about coordinate systems. Okay, so once we have a coordinate system, once we have two coordinate systems essentially, then we can define what is called a rotation matrix that holds between them. Okay, so this is an important concept. Essentially, I remember I told you that we are going to keep track of how there is a world frame, and how there is a rigid body here, and a coordinate system that is installed on this rigid body, zb, yb, xp, right? Now, and I told you that we are going to keep track of how these set of vectors essentially move with respect to those set of vectors. And what do I mean by move? Well, there's a translation motion of this coordinate system with respect to that coordinate system that can be kept track of by just looking at this position vector between the origins. That's simple. But how about rotation? How am I going to quantify a rotation? Turns out, the way to quantify rotation is to look at the dot products between the individual unit vectors that make up these coordinate systems. Okay, let me repeat that. The way we keep track of rotation of a rigid body with respect to another rigid body is that we keep track of the dot products, the dot products or the inner products between the unit vectors, or the basis vectors that make up the two coordinate frames. So, for example, I need to keep track of each of these terms, xp.xw, xp.yw, xp.zw. You see, these are all the dot products of the vector xp with the vectors that make up the world coordinate system. Okay? Similarly, I keep track of these, but similarly, I need to keep track of yb.xw, yb.yw, yb.zw. Okay, I also need to keep track of zb.xw, zb.yw, and zb.zw. Okay, so there are nine real numbers that I need to keep track of during the motion. Okay, and the knowledge of these dot products is going to tell me how the body coordinate system rotates, or the body rotates with respect to the world coordinate system. Okay, and we have a mathematical notion to express such system of numbers nicely, we essentially, all we do is encase these things into two square brackets, and we call this thing the rotation matrix of the rigid body with respect to the world, or RWB. Now, this is a matrix. You can think about this as a matrix, right? This is the 1, 1 element, this is the 1, 2 element, this is the 1, 3 element, this is the 2, 1 element, this is 3, 1 element, this is 3, 2 element, etc., right? You can view it as a matrix. And once you view it as a matrix, there comes along with that view some additional properties, okay? So, one property is that if you think about this in a linear algebra, abstract linear algebra type of way, right? What do matrices essentially signify? Why do we essentially care about matrices so much? The reason is that matrices are linear maps in disguise. Okay, so if you have a map that goes from a one vector space to another vector space, right? And you put some basis vectors that span and minimally span these vector spaces V and W, then to every such linear map F, every such linear map, there corresponds a matrix. And this is conversely true as well. To every matrix of proper size, of course, right, there corresponds a linear map between V and W, okay? So essentially, what am I trying to say? Essentially, we can think about this rotation matrix as a transformation, okay? Essentially, they act on vectors and transform them to other vectors, okay? And that transformation is actually physically meaningful. How is that physically meaningful, you might ask? Well, and that's going, let me stop here and make that the subject of the next video.